Hello everyone. Let's try this. Okay. I think it skipped a few. Yeah, there it is. Some mouse in the middle. Yeah, okay. Guess we can work with that. So welcome to our talk about typed messages and bridging between DORA and ROS2. So there's the screen. So we start with a short introduction to ROS2 and DORA, and then explain why we want to create a bridge between the two. Then we focus on some implementation details, including how to publish and subscribe messages from DORA to ROS2, and how we auto-generated Rust structs that match all the ROS2 types that we need to use. And then we also explain how we created the Python API. We also already saw some information on interacting between Rust and Python, and we will build on that to also bridge Python code to ROS2. And finally, we will show a usage example that shows how the different parts interact with each other and how we create an easy-to-use bridge in the end. Let's start with a short introduction to ROS2. ROS2 is a robotic framework for example, for creating autonomous driving, and it stands for robotic operating system. It's mainly focused on C++ and Python, and the idea is that the different processes act as nodes in a graph, and the nodes communicate with each other by sending messages. And for sending these messages, ROS2 mainly uses DDS. DDS is short for Data Distribution Service. It's a communication protocol which takes care of delivering messages, but also takes care of discovery of other nodes. And ROS2 is widely used in academic and industry. So there are also lots of existing tools that work with it. For example, there's Arvis for 3D visualization, and there's ROSBAC for recording and playing back messages. DORA, on the other hand, is a new robotics software framework that is written from scratch in Rust. And our goals with DORA are that we have native support for more languages, including Rust and Python as the primary ones, but also for C++ and C, and maybe WebAssembly in the future. In general, we try to be as high performance as possible, and we employ zero copy to avoid the overhead of passing messages on the same node. There will be a later talk about how we implemented this. One specific focus of DORA is that we focus on a simple build system. The idea is that you should not need to install additional software. You just use the normal package manager of the language that you're using. So if you're using Rust to create your nodes, then you should just add a simple cargo dependency. Or if you're using Python, you can use one of the Python package managers, such as pip, for example. And we try to be flexible and unopinionated to support as many use cases as possible. However, we're still in active development. So many features are still missing or still experimental. And we don't have all the fancy tooling that ROS2 has right now. So that was one of the motivating points for creating a bridge. So the idea is that by passing all the messages from DORA to ROS2, we can use the existing ROS2 tooling to inspect them, for example, or to use ROSBAC to log and replay them. And we're also compatible with existing ROS2 systems. So often there are large systems that are written in ROS2, and it's not feasible to port them all at once to DORA. So to make adoption easier, we want to have this bridge so that you can port the nodes one by one. And finally, there are also device drivers that are written exclusively for ROS2. So you need to either try to port them, or you can use the bridge to just use them from DORA, which is the easier approach. Then let's dive into some implementation details. So we will talk about publishing and subscribing to ROS2 and how we implemented it in our DORA ROS2 bridge. And then we talk about typed messages and how we automatically generate Rust structures to support these type messages in Rust. And we do that by passing the message definition files of Rust 2. And finally, we provide a Python API that makes it easy to use Rust 2 from a Python node in DORA. So for publishing and subscribing to Rust 2, we basically have two options. We can either link directly to the Rust 2 libraries, and this way we get like the official publish and subscribe implementation, but we also get access to all the advanced functionalities such as actions, services, and so on. However, this makes the build process quite complex because you need to have Rust 2 installed, have DORA installed, have Rust installed, CMake installed, everything on the same machine and the matching versions, and you need to link everything together. So this is getting very complex quickly. And also the interface of the library of Rust 2 might change between Rust 2 releases. So we only could support specific Rust 2 releases this way, and we would have additional work for every new Rust 2 release. So instead, we went with option B, and the idea is that we interact with Rust 2 nodes at the DDS level. So we interact at the middleware level and keep the two components completely separate. So we compile Rust 2 as usual, we don't modify anything there, and we also compile our DORA code separately using Cargo, for example. And then we use the network interface to basically act as if we're a Rust 2 node. And this way, the build process is much simpler, and most importantly, we can also pre-compile parts of it, which will become important for the Python API in the future, because Python often is shipped with, Python often ships pre-compiled binaries through package managers. However, using this approach is difficult to support advanced features because we need to act exactly as one of the Rust 2 nodes. So actions, services, and stuff like that, it's difficult to emulate this perfectly. But since we're mostly focused on basic publish subscribe messages for our bridge, we went with option B. And fortunately, there were some crates already for that called Rust CDS and Rust 2 client, which make this quite easy. So to publish messages to Rust 2, you need also to supply a type, because all messages in Rust 2 are typed. And the message format that they use is called Common Data Representation, or CDR for short. And it basically describes how a struct is laid out on the line, like serialized to a byte stream. One challenge is that the CDR format is not self-describing, so the actual message does not contain any type information. So you need to know which type the message is in order to understand it. And to implement this or to support this, Rust 2 client, this crate, uses the 30 traits. 30 is like a popular crate in the Rust ecosystem for serializing and deserializing data. And it provides two traits, serialize and deserialize, and you can easily derive them for any struct you define in Rust. So in this example, we have an example message with two fields, and we just add the two annotations, and then it's serializable and deserializable. And it's laid out exactly as defined, like in that order. It's important, however, that we match the format that Rust, like the Rust 2 nodes expect exactly, because otherwise the Rust 2 nodes will not be able to understand the message. So it's very easy to make mistakes when manually defining these structs. Because of that, we want to auto-generate all of these message types, and we can do that by looking at the Rust 2 message files. Because Rust 2 defines all message types in a so-called message definition file, which is a file with an MSG ending. And for example, there's this twist message example, which is just a struct with two fields, linear and angular. Both are of type vector3. A bit in the way here. Maybe on this side it's better. And vector3 references another message file called vector3.message, and there we see, okay, it's three floating point fields, x, y, and z. So as you see, the format is relatively simple, so it's possible to pass it automatically. And there's already a crate for that again, so we can use this RCL Rust message generator crate, which will take these files and extract all the type information that we need. So the last thing that we need to do is to somehow find these message files. And we can do that by reading the amend prefix path environment variable, which basically lists all the directories that contain ROS2 package files, including these message definition files. And this variable is automatically set up when you enable a ROS2 installation. So I don't know if you worked with ROS2, but one of the setup steps is to source the setup.sh file in your shell. And this will, among other things, this will set this environment variable. So we can just, in our bridge, when you build the bridge, we can read this environment variable and split it at the colon to get the individual paths of the packages. And one nice thing about cargo build scripts is that you can instruct the compiler when you want to rerun the build script. In this way, we can tell the compiler, please recompile it if either the environment variable changes, so if you add a new path to it because you add a new ROS2 package location, or if any of the packages within these paths changes. So if you, for example, modify like the twist message and add a third field or something. And this way we can ensure that our automatically generated code is always up to date. You don't need to manually clean anything because the Rust compiler will automatically decide, okay, now I need to rerun the script. Yeah, and the generation of Rust structs is relatively straightforward. So we want to create a separate struct for each message type that references the other structs. We use submodules to avoid name collisions. So we model it like the package, like the namespaces that are used in ROS2. And we can automatically add all the required derive attributes, including the serialize and deserialize implementations. For implementation, we use the quote crate, which is typically used for proc macros. So the idea is that you can you have this quote macro, and there you can define Rust code, which is then passed basically directly, and you get a token stream back, and this token stream can then be injected into the crate using a proc macro. So I think there's also a talk about this macros 2.0 later. I think this might be related to this. In general, the advantages of doing it this way is that we create the code at compile time. So it's already available when your editor, for example, tries to do autocompletion. So you get all the nice autocomplete support with field names and so on. And also the documentation that you create includes all packages and all of their, like all message types and all of their fields. So for example, it looks like this for our twist and vector3 messages. So we see these are normal Rust structs with 2 fields as expected. And we see that the floating point fields are converted to the matching floating point type in Rust, a 64-bit floating point type. Yeah, then let's do a first example. And let's try to move the turtle in this ROS2 turtle simulator. I think I put a picture it on the ROS2 slide. It's like a blue screen, and you have a turtle in it, and you can instruct it to go into some direction. So it's part of the ROS2 tutorial. And we can now use or move that turtle from our Rust code, from our DORA code. And for that, we first create a context and create a new node. We give the node a name and a namespace. And then we can publish a direction command. First, we need to create a topic. Yeah, let's maybe go here. So we first create a topic, give the topic a name. So this turtle CMD eval is the topic that the simulator listens for on movement messages. And then we create a publisher and specify the type that we want to publish. And then we can use our generated twist and vector3 structs to create a message and use the publish function to send it out. And this will connect to ROS2, detect all the nodes that are there, and publish it to the right one. And subscribing is also quite simple. We just need to specify our topic name again. In this case, we want to subscribe on the position. And yeah, thank you. And we need to specify the type here too, because otherwise we won't be able to read the messages. So here, this in square brackets, this pose is important because otherwise we wouldn't be able to make sense of the incoming messages. We need to know the type in order to read it. And then once we specify that, we can use the take function, for example, to wait for the next message and read it out. Yeah, let's talk about Python then. So in general, we try to reuse the Rust implementation to avoid any code duplication. And as we saw, we can use the Py03 create for interacting between Python and Rust code. So here's a simple example again. You annotate a Python function, a Rust function with the Py function attribute, and then it's callable from Rust. So here we just sum up two numbers and convert them to a string and pass them back to Python. And one thing that is important to mention is that Rust dependencies of Python code are often precompiled on different machines. So if you publish a package to pip and you have a Rust dependency, then this dependency will be precompiled on your build machine. And then if you use it later on a different machine, then you will just download it. So it's not a good idea to do a compile time message generation here, because we are interested in the message types of the machine where it's used, and not in the message types on the machine where it's compiled, right? So in this case, we need to modify the behavior a bit and do the parsing at runtime at the point where the ROS2 context is initialized. The second challenge about Python is that the Python type system is quite limited, so we're not able to represent all types that ROS2 supports. And this is a challenge because we need to know the exact type and need to use the correct type to serialize and deserialize correctly. So for example, ROS2 typically uses struct types to describe messages, but there is not really a struct type in Python. Instead, you have object. But object is actually a dictionary under the hood, and structs and dictionaries need to be serialized in a different way. So we need some additional metadata to serialize it. So the approach is the following. When we create a topic, we also need to pass in the type name that we want to publish, and then we can use that type name to look up the type information. And using that type information, we can then choose the correct type for serializing and deserializing. So let's do it in a bit more detail to make it clearer. So we wrap the value that we receive from the Python publish function in a new type value struct. So this struct has two fields. Value is the value that we got from Python, and type info is the type information that we got from parsing the ROS2 message files. And we match that based on the type name that is supplied. And then we can provide a custom implementation of the serialized trait and guide this implementation by the type information. So if the type information says that the topic expects a struct type and the user supplied a dictionary type, we still serialize the dictionary as if it were a struct. So that this way it looks correct on the line. And another example is integer precision, because in Python you only have one integer type, but for ROS2 it is important to use the correct precision. So if ROS2 expects an 8-bit integer, then we need to convert the Python type to an 8-bit integer before publishing. For serialization, it's kind of similar. We want to use this type information for deserialization, so we also require it when creating a topic. But one challenge is that the deserialized trait in its standard form doesn't support any additional runtime arguments. But we only know the type info at runtime, so we need to use something different. And this thing that we need to use is called deserialized seed. It's also included in the 30 crate, but it's much less used in the ecosystem. And it basically supports deserialization using an additional seed argument. And this argument we can use to pass in our type information and correctly read out the message. Unfortunately, the upstream ROS2 client and ROS-CDS crates don't support this deserialized seed crate yet, so we needed to modify the crates. And we're currently still minimizing these changes and plan to upstream them to hopefully make this deserialized seed trait more used in the Rust ecosystem. Yeah, then let's finish with an example of how all these components play together. So first we want to publish something to Rust2 using Python. As with the Rust code, we first create a context. This time, this will also, behind the scenes, pass all the Rust2 message files and take track of the types. And then we will create a new node, again with the node name and the namespace. And for the topic creation, we now support and require an additional type name. So in this case, we specify that we want a twist message. And this allows the publish function to look up the correct type information. Because of that, we can supply the direction as a normal Python dictionary. So we don't need to do any structs or anything specific. We just need to match the field names. And the publisher that we create then will automatically convert it to the right struct type when sending it out. And it will also fill in default data for fields that we haven't specified. And subscribing works kind of similar. We just need to specify the type name in the subscribe or in the topic creation. And then we can subscribe to this topic and use a normal for loop to receive all the messages. So again, we try to make it as simple to use as possible. In this way, you should be able to create nodes that act as bridges between Rust2 and DORA. And hopefully, we'll also provide ways to make this even simpler or even more automatic in the future. Then thank you for listening, and let's continue with the next talk on DORA drives, I think, right?